Hi, today I'll be talking about how we can use AI assistants to help us teach humans motor control tasks, such as riding or parking a car, in a more reliable and consistent way. Humans need to perform a variety of motor control tasks in our everyday lives, from personal enjoyment like sports, and even everyday tasks like riding or tying a shoelace. However, many motor tasks are challenging to learn, often taking years of practice for those who even have access to specialized instruction in the first place. Furthermore, motor control tasks are even more challenging to teach others. There may be many people, such as parents or friends, who are able to perform a motor control task well, such as playing the piano, but teaching it to someone is an even harder task for them. That's because teaching requires task understanding beyond rote memory, good communication ability and lesson design, and an awareness of the individual student's capabilities. Furthermore, this problem will only become worse as we introduce more novel control tasks, especially in the realm of human AI coordination. For example, semi-autonomous vehicles might introduce a new kind of control task for humans who now need to learn when and how to intervene and take over a car quickly in unsafe situations. Or in assistive surgery, humans now need to learn how to operate new control interfaces and how to augment the robot's capabilities in the most safe way. So, what makes teaching motor control tasks so challenging? First, they often require specialized instructors, like piano teachers, who know the task beyond rote memory and well enough to communicate and explain how to perform the task to others. Second, there are strong individual variations among the students learning the tasks, such as their height or arm length or left and right hand preferences. And then finally, there are also diverse physical conditions in the task, such as a patient's body during surgery, and we need to design curricula that can help us teach human students to be more robust towards these different conditions. So in our work, we imagine a new application for AI assistive systems, helping humans learn motor control tasks. Prior work on digitalization and education has already been embraced by many organizations. A popular one is Duolingo that helps increase access to teaching resources for simpler domains like language learning. Diving deeper in Duolingo, let's see exactly how tech assistants can be used. We first have this notion of skill identification, where the task is broken down into the relevant skills needed for learning. Then we have this notion of automatically identifying the weakest skills for an individual, which may or may not be the same as other students' weakest skills, as students differ in backgrounds and prior knowledge. And then finally, there's a notion of practice or curricular creation, which we refer to as drills, such as this exercise Duolingo provides the student based on their weakest words. So this process is a lot easier in common education domains, like mathematics or language learning, which prior work has studied. And that's because skills in these domains are well studied, standardized by different education bodies, and are also easy to detect, especially if the domain is text-based. But the key challenge for us is that motor control tasks is an entire trajectory over time, which is a much more complex data type. So let's see this on a new kind of motor control task, writing. In this case, learning how to write the Balinese alphabet script. There may be many experts who are able to perform this task well, but not many teachers familiar with how to teach this task to a new person. We can clearly see that this is a trajectory over time, which we can actually formalize as a Markov decision process with an initial state consisting of the starting xy coordinate, actions consisting of xy movements, and rewards consisting of how similar the student's writing is to the goal sequence that they wanted to write. And furthermore, we can introduce this notion of a scenario, which is the initial starting state and reward pair, so like the different phrases or sentences to write. And then a trajectory is a sequence of state action pairs that is provided for a particular scenario. So let's now be more formal about our three different teaching components, starting with skill identification. How do we identify motor control skills if all we have are the raw motion trajectories? Here we borrow from the RL literature a set of approaches for unsupervised skill discovery. And while our work is agnostic to the specific unsupervised skill discovery algorithm, we'll focus on a particular example, compile. Loosely speaking, compile is an autoencoder decoder based method that learns to break down expert trajectories or state action sequences for a task into different subsequences that are then reusable across the different trajectories and scenarios for that task. And specifically, there are two components. a boundary network that predicts the boundary for the next skill segment, and the encoding network that predicts the latent code for that segment. The decoder then, given a state and latent skill code as input, aims to reconstruct the action sequence corresponding to that skill, which is what the loss function captures. We can then train this architecture on an entire set of expert demonstrations to get a chain compile module. We could then take as input a trajectory for a new sequence, even if it was unseen during chaining, and output the different skills used during that trajectory and their respective boundaries. So, for example, here, we see that this horn-shaped stroke could be considered the same underlying skill by the compile module. So again, our key idea is that it is easy to find experts to perform a motor control task, or at least much easier to find experts than teachers of that task. And so we can combine expert demonstrations and unsupervised skill discovery algorithms to help us break down these tasks into skills. So now that we can identify skills in expert demonstrations, how can we identify individual skill expertise from student motion trajectories? Recall that we have access to a chain compile skill discovery model that can take an expert demonstration and break it down into its individual skills. What happens if we now give as input a noisy novice student demonstration that looks so different from an expert demonstration? Compile may not be able to detect all skills now because that human demonstration is not perfectly accurate like the experts. So we can now actually use this to determine which skills to penalize as the skills the student is struggling with. However, we also have this notion of a temporal ordering of skills. For example, here, if the student struggled starting from skill 2, they never actually really reached a state to attempt and perform skills 3 and 4. So we should reduce the penalty for skills that occur later on in the trajectory, because we don't really have a confident estimate of how well the students were able to perform that skill. And then we can control this via a temporal decay term. So specifically for this writing task, say we formulate reward as a combination of the pixel-wise distance between the student expert trajectory and how far along the x-axis student was able to write. And let's say it's a negative reward. Then we can distribute this negative reward across skills according to this penalty, such that the first skill the student struggles with gets the most negative reward assigned to it. So for example, with a reward of negative 12 and a decay penalty of 1, we have these final penalty scores for each skill. And if we show a diverse enough set of scenarios that together require a diverse set of skills required by an expert, then we can get a good estimate of what skills an individual finds most challenging. And we can formulate the selection of these diverse scenarios as a maximum set coverage problem. And so the key point here is that we now have this method for individualization, where each student has a unique set of skill penalty scores. And while some skills are universally hard, like skill 2 in this example, others might be difficult only for one student in particular. So now finally, how can we construct novel individualized drills or practice sequences that help each student improve learning given just motion trajectories? So usually in motor control tasks, we have this idea of drills, like in basketball, that are repetitive sequences that target skills in common contexts that are meant to help the person improve on that skill, rather than just simply practicing by performing the overall task, such as playing an entire basketball game. So given an individual, say we identified that they are particularly struggling with skill 1 and should improve on that skill. How can we create a practice drill? Well, we can first introduce a repetition parameter that controls for the degree of repetition in the drill. And then another key idea was this common context parameter. So how is the skill typically used in the actual task? And what are the transitions between that skill and other skills that are also necessary for the student to learn? So for this, we can introduce this context size parameter, and then given the data set of expert demonstration, find the most common context sequence of that size that contains skill 1, which is similar to finding common n-grams for those familiar with NLP. So then here's an example drill sequence that this student would have to practice skill 1. So to recap our overall assistive teaching approach, we first extract skills from expert demonstrations, then create a set of scenarios that require a diverse set of skills, which we use to get good estimates of a student's ability across different skills, and then use this to automatically create individualized drills. So now I'll talk about our experiments. We focus on two specific motor control tasks, parking a car and riding, and build web interfaces for both of them where students participated in a teaching curricula. For our writing task, the goal is for students to learn how to write different Balinese characters with a mouse control on our interface. For our expert trajectories, we used real human handwriting trajectories from the crowdsourced Omniglot dataset. And both the state and action space is continuous with 2 dimensions, just the x and y position and movement. For our second task, parking, we build upon an OpenAI gym environment where the goal is to park the yellow car into the parking spot marked by a blue square. And the user controls the car using the mouse control toggle on the screen. And the state space is a 6-dimensional state space corresponding to the car's position, velocity, and heading, and then the action space is 2-dimensional, controlling the acceleration and heading angle. So stepping back a step, recall that our entire method of constructing individualized drills is first built upon extracting skills from the expert trajectories for a task using this compile algorithm. So our first evaluation, our first experiment in teaching humans is asking if skill-focused practice is even useful at all. Do humans actually benefit from skill-focused teaching for motor control tasks, as was our initial intuition, or is it not necessary to focus on practicing individual skills? So to test this experimentally, we'll compare 3 different modes for the practice sessions in our user study. First, users practice completing the full trajectories across different scenarios. And if this mode turned out to be the best performing mode, then this would suggest that we don't really need to do anything fancy with skill discovery algorithms or drill construction. We could just let students practice different scenarios on their own. And furthermore, it would say skill-focused practice is not really important. Just getting familiar with the task itself is important. Next, we consider a time heuristic for determining skills. And concretely, for each scenario, we split the expert trajectory into 3 segments equal in terms of the number of time steps, and name the first, second, and third segments Skill 1, Skill 2, and Skill 3 respectively. For tasks where skills are often consistent in their temporal order and equal in length, then this heuristic could do well. And if this heuristic does lead to strong learning outcomes, it would suggest that we don't need to use an AI-driven method for skill discovery and can just implement a very easy heuristic, a hard-coded heuristic. And then finally, we consider skills outputted by compile. And note in the parking example, compile kind of isolates the entire turn the car is making, rather than cutting it off in the middle like the time heuristic does. We then conduct a user study with participants recruited on the prolific crowdsourcing platform, comparing these 3 practice modes. And specifically, we measure users' reward improvement, which is the difference in average reward between their evaluation rounds and their pretest rounds conducted before the practice sessions. And we find that for both of our tasks, skills returned from compile lead to significantly higher reward improvement than practicing with the full trajectories, supporting our hypothesis that skill-focused practice leads to stronger learning outcomes. Furthermore, the time heuristic for selecting skills is notably inconsistent. While it is almost as helpful as compile skills for the writing task, it leads to very low reward improvement for the parking task. And this supports our goal of using AI assistance for skill discovery as a way of providing more uniformity in the way we teach humans motor control skills. It's a way we can kind of be robust to the different types of motor control tasks we're trying to teach. So finally, given that we found skills returned from compile useful, we then ask whether our overall method of constructing those individualized drills that are based on these skills, do those drills ultimately help students learn? So again, we compare 3 different practice modes for human participants in our user study. First, from the last experiment, practicing with just the compile skills that were outputted directly. Second, practicing with randomly selected drills. And then third, practicing with individualized drills that target the skills that each individual student is struggling with as identified during their pretest round. And recall, our intuition for why drills are useful is that they help users practice skills as part of a larger context without actually practicing the full trajectory, and allow us to create these novel, repetitive sequences students may not have seen before. And our intuition for why individualized drills in particular are useful is that they help each student practice practice drills that target the skills that they are unique and struggling with and uniquely need to improve on the most. So here we show the distribution of skills identified as difficult skills for participants in our user studies for both tasks and example drill sequences for each skills. And the images show that for both tasks, there is a widespread and variety of which skills were found to be most difficult. For example, for the parking task, the two most commonly difficult skills for participants were reverse actions. And so the individualized drills those students practiced particularly targeted reversing. However, there were still some students for whom sharp turn, for example, or even just kind of moving stably in a straight direction was the most challenging skill. Then we measure both reward improvement and user-reported helpfulness of the practice sessions across all three practice modes. And overall, we find that for both tasks, individualized drills generally improve student performance compared to the other modes. Furthermore, for the writing tasks, participants significantly found individualized drills more helpful for learning. However, for parking, we found the opposite. Participants significantly preferred skills over individualized drills, despite performing better with individualized drills. To further explore this, we studied the evaluation rounds where the optimal expert action was to reverse. And recall that we had identified skills involving reverse actions as the most common skills students struggled with, which suggests that most students received drills and practice sessions that targeted reversing skills. And in fact, we find that students who only received skill-focused practice sessions or random drills attempted to reverse only 27% of the time during evaluation, even when the optimal expert action was to reverse. Meanwhile, students who did practice with individualized drills attempted to reverse more than half of the time, showing that the instruction did help those students learn to perform the more optimal action. However, as this video shows, reversing is a tricky skill, and participants found it hard to retain control fully, likely leading to lower self-reported scores. And so this raises an interesting question of what is the right way to assess successful teaching, as our parking task showed a conflict between user perception and performance. Overall, our results show promise for AI-assisted teaching of motor control skills based on individualized drill construction. To re-emphasize, the key idea is that it is a lot easier to find experts who can perform a task well than it is who can find people who are expert at teaching and who can explain and teach the task well to others. And so therefore, our method is that we can take data from any expert, a human expert, a synthetic agent, and create a reliable way for teaching that task to humans. And we overall show that participants did indeed benefit from AI assistance for two very different control tasks. However, our method of using skill discovery algorithms opens many important directions for future work. And one important direction is building stronger models of student motor learning so that we can test out different hypotheses, different ways of bringing down skills, and different learning curricula to better understand what method makes humans learn the most efficiently or rather long term. And we made an initial attempt in our paper with synthetic imitation learning agents, but imitation learning isn't really the way humans learn such tasks, and it would be greater if we had a better cognitive understanding about how humans learn motor control tasks. And then another important direction is considering what happens when there is an expert-student mismatch, where the way the expert attempts to do the task differs from how the student wants to learn how to do the task. For example, one user study participant commented that while they enjoyed the tool and concept for learning, the exact control method was difficult due to their disability. Some methods for estimating students' control preferences before developing the practice sessions would be a promising next step. And that's it. Thank you.